I'd appreciate it. We record? Yeah. Okay, so today we finally get to do the thing. The thing is, we have an integral and we come up with an answer for it. Kind of two parts to think about from Friday. It's kind of like putting two different things together. We basically did in the first part, we saw the fundamental theorem of calculus. Oh, usually that's not lagged like that, but today it is. So basically what an integral does is it tells you how much change happens between your two x values. So whatever, if there's a story problem that goes behind it, I think in ours, do we have water in a bucket? That sounds like something. Yeah, water being collected in a rain bucket. So when we integrate the rate at which that water is falling in the rain bucket, we find how much rain actually fell in the bucket between the two time periods. And the fundamental theorem of calculus basically tells us that we need to look at the function in our integral, find an antiderivative, and then plug in those two values, the starting value and the ending value. So it looks a little innocent, all I have to do is f of b minus f of a. But the thing is, we are integrating a function and we're plugging into its antiderivative. So the two steps will basically be find the antiderivative and then plug the numbers in. So let's do a couple examples of those. So we are, wow, I don't know what's up with that. I think I just need to reset this computer. It hasn't been reset in a month. So what we're going to do, two steps. Find an antiderivative, plug in both numbers, subtract. We've got to be really, really, really careful with our signs, and I will try to do a good job of consistently showing that there are two parts of this problem. For example, in number one, plugging the 4 in and then plugging the -3 in. So we need an antiderivative for 4 minus 6x. The rules that work well for derivatives work well for integrals. So adding and subtracting can be separated. Coefficients are just coefficients. Linear shifts are just linear shift, or sorry, not linear shift. Horizontal shifts are just horizontal shifts. Those are the big three that we kind of don't have to worry about. Everything else is difficult. Not difficult, but it is not what we would expect it just to initially be. And you'll see when we get into the other, some of the things we have to do with integrals, it's actually even more complicated working backwards than it is working forwards. But let's start with something easy. Antiderivative for 4 is 4x. So our antiderivative we're going to use is going to start with 4x. And an antiderivative for negative 6x, 3x squared. So negative 3x squared. The notation we use looks like this. We draw that evaluate at bar, and we just plug in our -3 and our 4. Not plug in, but we write them there. So the same order they are on the integral. We go top to bottom. When we read it, we're saying that we're integrating from -3 to 4, but now when we plug in that upper limit, the 4 first. So you've got to come up with two things, and they need to be subtracted. It's smart to write this out at first. You know you're going to have two numbers there because you've got to plug into 4x and minus 3x squared. So we'll do, and we're just going to do that. We're going to plug in. 4x would be 16 minus 3x squared. That's 3 times 16. So that's going to be 48. And then in the second set of parentheses, we'll plug in the -3. Maybe I'll do it this way. I like this color coding. So now we have -12 minus, and I think we have 27, 3 times -3 squared. Yep, cool. I don't know. I haven't done it yet. What's that? Yeah, you're squaring a -3, so yep. All right, so we end up with, I hear a calculator lid that we don't need, -32 in the front, -32 in the front, and 39, but positive in the back. So just 7. Boom. The area under that curve between -3 and, well, not a curve, it'd be a straight line. We could actually, have drawn this out and figured it out using triangles and rectangles and things like that, but we didn't. The area under that curve is 7. If that 4 minus 6x represented a rate of change of something, that something would have changed by 7. It would have increased by 7 during that interval. Okay, number 2, integral from 0 to 9 of square root of x plus 1 over x plus 1. Same thing, it's addition and subtraction there, so we'll treat them separately. Square root of x is x to the 1/2 power. X plus 1 over x plus 1 is x plus 1 to the -1 power. That is the thing we need to find the antiderivative for. So 2 parts to it. We need a coefficient and we need a power for x to the 1/2. What's the power? It's currently 1/2. Sorry, when we integrate, what's the power? 3/2. And then what's the coefficient? Not 3/2. 2/3, because you have to divide by 3/2. Yeah. So yeah, new power, divide by that new power. Whenever that power is a fraction, just multiply by the reciprocal. So you got 2/3 x to the 3/2 plus, okay, yeah, no, we're good. X plus 1 to the -1 power. Is that power rule?
I've seen videos of people x squared or third.
Yeah. So if we use power rule, the new exponent is the new exponent, 0, and then we divide by, can we divide by 0? No. X plus 1 to the -1, that -1 power is the only one that isn't the power rule. What function has a derivative of 1 over x? ln x. So this is the ln of the absolute value of x plus 1. So it's something to watch out for because it's it feels like power rule. But if you actually execute the power rule correctly, you will get the wrong, you'll get something that doesn't work. Yeah. We are integrating from 0 to 9, and when you plug in from 0 to 9, that would be positive anyway. So those absolute value bars, I'm not saying don't put them there, but they don't really serve a purpose. So we need to integrate this from 0 to 10. I'll make my bottom one blue. All right. 0 to 9. Yeah, sorry, I was one step ahead of myself with the, because it's x plus 1, I was thinking in my head. Anyway, so let's do it. We should have 2 parentheses, a minus in between them, so we just avoid making little mistakes. We got a little bit of math to do in this parenthesis. I've got to do 2 times 3 times the square root of 9 cubed. I don't know why I put a parenthesis there. I don't really need it. Yeah. Remember, when you need to raise something to a power and root it, although it looks like, kind of just following it straight through, it looks like we should raise 9 to the 3rd power and then take the square root of that, but that's extra work. Take the square root first and then raise to the power. We have a lot of kind of things that work against each other in this problem. So the square root of 9 is 3. Raise that to the 3rd power, but then divide by 3. So I've got to do 3 times 3 times 3 divided by 3. But so I'm kind of showing a mental thing here because this is what I do. I'm just keeping track of how many 3s I have. I've got 3 to the 3rd power in the square root bar, but then I have a 3 in the denominator. In the end, all of that is just going to turn into 3 times 3, which is 9. And I've dealt with all of the 3s. I haven't dealt with the 2. Yep. So I end up with 2 times 3, which is 18. 2 times 9, which is 18. I knew I had 18. I just want to make sure I didn't make a mistake with that one. And here I have the ln of 10. Should do this in blue. The ln of 10 minus the ln of 1. And the ln of 1 is 0. Oh shoot! I'm sorry. No, I'm like I don't. I'm wrong. That's bad. Yeah. No, I'm sorry. That explains the looks because I wasn't thinking what the problem was. I got it. No, that should not be like that. My bad. So we were. That was when I yeah. So what did I have here? 9 cubed. This should be plus ln of 10. This is where the ln of 10 goes. Sorry about that. Yeah, no, that was just totally my mistake there. And now here, I got to plug 0 in, but 2/3 times 0 to any power is 0 plus ln of 1, which is 0. So this whole blue square root is just 0. And the only thing we have to clean up, and the only reason we'd have to clean it up would be if it was matching for multiple choice. If it was just a free answer, leave it like that, or, at least kill the 0 if you really want to. 2/3, what did I say? 2 times 9, we decided, plus ln 10. So 18 plus ln 10. Yeah. All right. So number 3, always look at your arguments. The only thing we know how to deal with right now are linear arguments. So x over 2 is a coefficient of 1/2 times x. Anything that's more complicated, sine of x squared, things like that, that is until later in the unit. So just linear arguments are the only thing we really know how to deal with. It's the same linear chain rule. In derivatives, you multiply by that coefficient. If you're working backwards, you divide by that coefficient. If that coefficient happens to be a fraction, we multiply by its reciprocal, right? All right, so we've got 2 things going on here. I've got a 4. That just comes along for the ride. I'm going to use the linear chain rule. So my coefficient is 1/2. So times 2. Yep. And we'll do, yep. Just to point out where it comes from, we'll multiply by 2. And an antiderivative of sine is negative cosine. Arguments never change. Don't write this because it looks like you're writing 8 times negative cosine. So either put it in parentheses or just bring it out to the front, whatever works best for you. And we're going to do that from 0 to pi. Okay. So, there's different ways to treat this. You can leave the 8 on the outside. I'll do it that way. You could also just consider it as negative 8 cosine and have 8 in both spots. I'm going to leave my 8 on the outside. When I do that, though, I need to do this. Right? So 8's on the outside of that subtraction. Make it negative. Be smart about this. And now I just have cosine pi over 2 minus cosine 0 over 2. Negative 8. The cosine of pi over 2 is 0. The cosine of 0 is, which makes my answer correct answer. Practice. This is going to be practice. We're actually going to, we'll do this. We'll finish up our things here today. We'll have this assignment. And tomorrow I actually have an extra sheet just for practice of this. So that's kind of our plan going forward with that. We have 2 more examples to look at, though. Yeah. All right. The fundamental theorem of calculus is a theorem. Theorems have conditions. We saw that a lot with IVT and MVT because we had to literally write out those conditions. The condition for the fundamental theorem of calculus is that your function needs to be continuous. If your function isn't continuous, then the fundamental theorem doesn't work. What's going to happen here, though, is if you have a piecewise function, you're just going to break it up into its continuous parts. And as a matter of fact, even if it's not continuous, you wouldn't be able to find an antiderivative anyway if it weren't for its, you wouldn't be able to find an antiderivative for a continuous function. So you have to break it up into its parts anyway, but you can still use it. So we have a function that's 5x squared when x is less than 1, and we have a function that's just the constant function 3 when x is greater than 1. Is that function continuous?
Yes.
Okay, prove it. It is not continuous is the revised answer. How do we know it's not continuous? It's a jump. But using calculus, how do we know? We do have to plug in for x for both of those. And what notation should we use when we plug in x for one? Limit. Yep. Yes. The limit as x approaches 1 left of f of x equals 5. And the limit as x approaches 1 right of f of x equals 3. So the limit as x approaches 1 of f of x does not exist. Look at you guys remember in September. Remember when limits were hard? That was a refrain my first year doing this. Said many times. Okay. Yeah, there's so much that we've piled on top of it. So I'm just going to tiny this up a little bit so it's out of our way. So yeah, this is not continuous. But honestly, if it's piecewise, no matter what, you have to do this. I just wanted to kind of see if we remembered any of that stuff. So what we're going to do is we're actually going to do 2 integrals. We are going to integrate from -2 to 1 of f of x. And then we're going to integrate from 1 to 4 of f of x. And we're going to solve those 2 separate integrals because those have antiderivatives that are just power rule. Okay. So this is all really new to you. For me, this feels like second nature, but make sure you understand how I'm doing those numbers, right? From -2 to 1, and then from 1 to 4. It's really common, and we'll see this when we get to limit properties later on. It's really common to have that same number kind of end one spot and start the next one. That's just breaking it up into 2 pieces. You could actually do this with any integral, and it would still work out. It would just be more work. Okay, so an antiderivative for f of x when you are less than 1 would be what? You're close. 5x cubed over 3, or 5/3 x cubed. And that's going to be from -2 to 1 plus, much easier, antiderivative for 3, 3x from -2 to 1. So we actually need 2 sets of parentheses. They don't need to be super big because it's only one thing. Alrighty. So let's see. We need to plug in 5/3 x cubed if it's 1. So that's going to be 5/3. We've got to plug -2 into x cubed, which is going to give us -2 cubed, -8 times 5. Yeah, thank you. Yep. So we got -8 times 5 is -40 thirds. It's actually going to turn out to a whole number. And then much easier on the other side, 3 times 4 is 12. Just make sure you have the right numbers, unlike me, -3. So we've got 2 separate fundamental theorem problems. But we end up with 5/3 plus 40/3 on the left part of it. That's going to give us 45/3, which is 15. And then we've got to add that to 12 minus 3, which is 9 last time I checked. And by 26, you mean correct, because we're adding 9, not 11. Okay. And of course, our old friend, the absolute value. Absolute value is a piecewise function. It is your job to write it as a piecewise function. at what value do I have to separate this? 3. Yep. So this equals a piecewise function, and you do something different when x is less than 3, and you do something different when x is greater than or equal to 3, and it does not matter where that equal bar goes, because when you plug 3 in, you get the same result no matter what, because 3 minus 3 is 0. So your choice on where you want that equal bar. So if I plug in something smaller than 3, this will be negative, which means I have to multiply by an extra negative 1. So it's negative x plus 3 plus 1, negative x plus 4. There. Cool. Negative x plus 4. And then on the other side, I do not have to do anything because my absolute value will be positive. So it's just x minus 3 plus 1. So x minus 2. Cool. So 2 separate integrals. Get it right this time from 0 to 3. I got the integrals right. It was the other part. Even if it were, you wouldn't be able to find an antiderivative that works across the whole function, so you still have to split it. I know, but I introed it that way, so I think that's a legit question to ask. So we go from 0 to 3 of negative x plus 4 dx. I missed my dx over here. And to that, then we're going to add the integral from 3 to 4 of x minus 2 dx. So we have negative x squared over 2 plus 4x. Positive x squared over 2 minus 2x. All right. You guys do the math on that, see what you come up with. Set up your parentheses. You should end up with 4 parentheses wide. You should have an addition problem in the first 2 parentheses. You should have a subtraction problem in the next 2 parentheses. Plugging 0 in is going to be nice. All right, guys. So here's what I came up with. We did end up with 2 zeros there. Plugging the 0 in was really easy. Anytime you have something that's just a polynomial with x's in every term and you plug 0 into it, you're going to get 0. Careful not to get in the habit of that. Every once in a while, you'll miss something. Make sure it actually gives 0. The way the other side worked out, when you plugged 4 in there, that just happened to also give you 0. So what you ended up with was in your first parentheses, negative 9 halves plus 12. And in your last parentheses, with a negative in front of it, you had 9 halves minus 6. But that was really negative 9 halves plus 6. I find, especially because sometimes things come out to whole numbers, that it's easier to deal with, if I see that I have 2 fractions with a denominator of 2, I'll hold off on trying to mix them with whole numbers until I get down to this step. Because negative 9 halves minus another negative 9 halves is just the number negative 9. There's nothing wrong with trying to figure out what negative 9 halves plus 12 is. That could get you the right answer, but I saw negative 9 halves. I saw that there was going to be another negative 9 or another 9 halves over here. So they were either coming together to give me something or they were canceling. But they didn't cancel because they had the same signs. Okay. All right. Last but not least, just to kind of work our way around the fundamental theorem. We'll do one problem by hand, one problem calculator active, and then you guys have at least 15 minutes to get some practice in. We'll see these types of problems over and over again, and we might even do them a slightly different. We'll definitely do them a slightly different way as we get a little bit better with this stuff. But in the end, it's the same. Know your function in this one. I think I wrote these purposely in using different notation. So A has slightly different notation than B. They're both correct, though. So we've got little f and big F that are functions such that little f of x is the derivative of big F of x. Little f of x equals capital F prime of x. That's not set in stone when you see letters like that. They have to give you that little extra sentence, but it is common to see it that way. We want to find f of 10 if little f is x cubed and big F of 2 is 50. So what we can do, we can use the fundamental theorem kind of to our advantage here, but it's kind of like we're putting something in the middle. So I know that the integral from 2 to 10 of little f of x dx is f of 10 minus f of 2. There's three pieces there. There's the integral, there's f of 10, and there's f of 2. I know what f of 2 is. It's 50, they told me. I have an integral that I can solve, and that'll give me a number. And then I have an algebra 1 problem. I think I'll go one step further here and erase the f of x. I was kind of thinking in terms of fundamental theorem and just replacing it with x cubed. Yeah. So that means that x to the 4th over 4 from 2 to 10 is equal to f of 10 minus 50. Probably should have set these up side by side so I'd have like vertical space on both, but that's okay. We'll just bring it up here. So I have 10 to the 4th over 4, which is 1,000 over 4. No, 10,000 over 4, right? Minus 2 to the 4th over 4, which is 16 fourths. Oop, I don't know where that 1 came from. Yep. Which equals AF of 10 minus 50. Oh. All righty. So probably easier to simplify in line. 16 fourths is 4. 100 fourths would be 25. So this should be 25 with 2 zeros after it. What's that? Yeah, that is, I thought maybe you put it in your calculator. All right. All right. So we end up with 2,500 minus 4, which sure sounds like 2496 equals f of 10 minus 50. So the f of 10 equals Yep. Yeah. There is a lot of area under the curve x cubed because it grows so fast. That's why that answer is so big. I don't know why I put a comma there. We never write commas. Yeah. But yeah. All right. We should be able to set this all up into Desmos in our next one and just basically have one line that answers our question. So let's get this set up over on our paper, and then we'll just get the answer right out of Desmos. So same thing. Our limits are f of 0 and f of 3. You'll notice I used capital F prime here instead of little f. They are one in the same. So if you integrate something that is prime, the antiderivative is the function itself. So the integral from 0 to 3 of e to the negative x squared dx equals capital F of 3 minus f of 0. We want f of 3. So let's solve this equation for f of 3. How about we do it correctly? F of 3 equals the integral, I was right, plus f of 0. So keep f of 3 on its side, move f of 0 to the other side, flip the sides in the process. Except we didn't want to solve for f of 3, did we? We know f of 3. Oops. All right, we want to solve for f of 0, so we need to move f of 0 to this side and the integral to the other side. So we end up with f of 0 equals f of 3, who didn't move sides, minus the integral 0 to 3 e to the negative x squared dx. But then we can replace f of 3 with the number 1. That's not an eraser. Boom. Cool. So literally, this is just a matter of going to Desmos and typing this in and getting a number. So I will do that quickly. I will point out that Desmos hates raising to the x squared power, so we'll deal with that. 1 minus, you just type in the letters int, which I don't have. I do. int, boom. Back to my numbers, 0 to 3. E to the, was it negative x squared? Yeah, that's what I thought. E to the negative x squared. When you stats people do the normal distribution, this is the integral with the coefficient. Yep.
So they don't actually.
As I say, yeah, they don't tell you that. You don't even need the right numbers. All right, so it looks like our answer is 0.114. Agree? Did I type anything? Did I type that all incorrect? Cool. Yep. Yeah, if I tried to do e to the negative x squared without those parentheses, it would yell at me. And by yell at me, it would just put the 2 not where I wanted it. And then I'd have to be, yeah, I think it would do something. What does it do? It's annoying. No, when we set up an integral, there's nothing saying this has to happen, but when we set up an integral, we integrate from the lower number to the higher number. And then when we plug in the top number minus the bottom number. As long as we're consistent with that, there were 2 ways to write this one out. But yeah. Oh, you know, maybe because I have the squared button, but if I was doing that on my computer keyboard, that's where it would argue with me with that squared. But yeah, but I would have these push buttons here. It didn't dislike it. Doesn't matter. As long as you get it in, that's the key. I was just giving you a word of warning about sometimes it not liking those things there. So, wrong one. Is that what we want? Yeah. So f of 0. Okay, apparently I'm not allowed to write anymore. So equals 1.114. Oh yeah, that's on my computer though. Yeah, that was like on the computer, not the tablet. I don't know why the tablet's being. It's like doing. I don't know. I don't need to write anything else though, so we're good. Deal with it later. That's later me's problem. You just write 0.114 and take the 15 minutes or so to get some practice here. 0.114, right from Desmos. Alrighty. Stops.